Let's get right to it. What are you made of? What is this screen made of? What is the entire universe made of? We're going to break it all down to the absolute fundamental building blocks of everything.
Seriously, it's the biggest question there is, right? If you could just keep zooming in past anything a microscope could ever show you, you'd find that this incredibly complex, diverse world we live in is actually built from just a tiny handful of basic ingredients. So let's meet them.
Everything starts with just three core particles. You can think of them like the primary colors that an artist uses to paint an entire masterpiece. And the entire cosmos is that masterpiece. First up, let's look at the particle that gives everything its identity.
Okay, so this is the proton. It's got a positive charge, and it lives packed really tightly in the very center of an atom in a place we call the nucleus. Now, this is the key takeaway. The number of protons an atom has is what defines it. It's that simple. One proton, that's always hydrogen. Got 6 protons? You're looking at carbon. It is the atom's unique fingerprint, a concept we really started to grasp thanks to the work of Ernest Rutherford.
Next, we've got the electron. It's kind of the proton's opposite. It's negatively charged, and it's not in the nucleus. Instead, it's zipping around the outside in this kind of cloud. First pinned down way back in 1897 by J.J. Thomson, the electron is basically the social butterfly of the subatomic world. It's responsible for all chemical bonding. You know, how atoms link up to make molecules, which in turn make, well, everything.
And to round out our trio, we have the neutron. Just like the proton, it's hanging out in the nucleus. But, as its name kind of gives away, it's neutral. No charge at all. Its existence was confirmed by James Chadwick back in 1932. The neutron's big jobs are to add mass and act as a kind of nuclear glue. It keeps those positive protons from pushing each other away and making the whole atom fly apart.
So let's recap our team here. You've got the positive protons and neutral neutrons huddled together in that dense core, the nucleus. And then you have the negative electrons orbiting way on the outside. Different charges, different locations, and all discovered by these brilliant scientists. But I keep saying that core is dense. Just how dense are we talking?
Okay, check out this number. This is the mass of a single proton or a single neutron. In kilograms, that's a decimal point, followed by 26 zeros, and then the numbers 167. It is an unbelievably small number, but almost all of an atom's mass comes from these two particles. They are the true heavyweights.
Now look at the mass of an electron. It is almost 2,000 times lighter than a proton or neutron. To give you some perspective, if a proton was the size of a bowling ball, an electron would be lighter than a single grain of sand. And that's why electrons contribute basically nothing to an atom's total mass, even though their role in chemistry is so incredibly important.
So, we have our 3 particles, right? 2 heavyweights and 1 super lightweight. Now, let's see how they come together. There's a pretty simple set of rules for how they assemble to build a complete, stable atom. The assembly process is actually beautifully simple. The heavy guys, protons and neutrons, they form that dense nucleus. The lightweight electrons orbit that core. The number of protons, that's the element's atomic number, that gives the atom its name and identity. And for the atom to be electrically neutral, the number of positive protons has to be perfectly balanced by an equal number of negative electrons. It's this perfect little dance of cosmic forces. But what happens when that perfect balance gets, disturbed? Atoms aren't always so static. They can gain or lose particles, and when they do, they transform into different versions of themselves. Let's dig into that. Okay, so if a neutral atom loses one of its electrons, it suddenly has more positive charges than negative ones. That gives it an overall positive charge, and we call that a cation. On the flip side, if it gains an extra electron, it gets an overall negative charge, and we call that an anion. The most important thing to remember here is that it's only the electrons that are coming or going. The protons are locked safely away in the nucleus. Now, an atom can also change its number of neutrons. Let's take carbon as a classic example. Every single carbon atom in the universe has 6 protons. That's what makes it carbon. Most of them also have 6 neutrons, so you add those together, 6 protons plus 6 neutrons, and you get a mass number of 12, carbon 12. But some carbon atoms have 8 neutrons, making them heavier, carbon 14. It's still carbon because it still has 6 protons, it's just a different flavor, a different isotope.
So, with all these different atoms and ions and isotopes running around, you can see why humanity needed a system to keep track of it all. This led to what is maybe one of the most beautiful and powerful tools in all of science, the periodic table.
Getting to the table we know today was quite a journey. Early scientists like Johann Wolfgang Dobereiner and John Newlands, they spotted some patterns. But the really huge breakthrough came in 1869 from a Russian chemist, Dmitry Mendeleev. He arranged the elements by their mass, but, and this was genius, he left gaps in his table for elements he predicted had to exist, but just hadn't been discovered yet. Then, the final piece of the puzzle came from Henry Moseley in 1913. He showed that the real organizing principle wasn't mass, it was the atomic number, the number of protons.
So now that we know how it's all organized, let's actually get to know some of these elements. We're going to meet the first 20 building blocks and see where they pop up in our everyday lives.
All right, starting at number 1, we have hydrogen, the lightest and most abundant element, the fuel of stars. Next is helium, the super non-reactive gas that makes balloons float. Then we get into some really reactive metals. Lithium, which powers our phones and laptops. Sodium, a key part of table salt. And potassium, which is absolutely vital for our nerves to work properly.
This next group, wow. These are the absolute cornerstones of life and our planet. You've got carbon, the backbone of every living thing. Nitrogen makes up most of the air we're moving through right now. Oxygen, of course, is the part we actually need to breathe. Then there's phosphorus, a critical piece of our DNA, and sulfur, which you'll find in everything from matches to fertilizer.
Then we get this group of really strong and incredibly useful elements. There's beryllium, a super lightweight metal used in aerospace. Boron, which helps make really tough glass. Magnesium is what burns so brightly in fireworks. Of course, there's the aluminum in our soda cans, and maybe most importantly for our modern world, silicon, the element at the very heart of every computer chip.
I love this group because it shows such an amazing contrast. On one side, you had these super reactive gases, like fluorine that helps protect our teeth, and chlorine that cleans our swimming pools. And on the other side, you have the completely chill, non-reactive gases, like neon, famous for its glowing signs, and argon, which is used inside light bulbs to keep them from burning out.
And that brings us to number 20, calcium. It's the element that builds the very bones in our bodies and gives the concrete in our buildings the strength to stand tall. A perfectly strong element to finish on.
And when you step back, that's really the magic of all this, isn't it? Protons, neutrons, and electrons. That's it. From just those 3 simple particles, mixed and matched in different numbers, you get absolutely everything. Stars, planets, life, even us. An entire universe of incredible complexity, all built from the simplest possible ingredients.
You know, our current understanding, all laid out so beautifully on the periodic table, accounts for 118 known elements. But science, well, science never, ever stops asking questions. So it really makes you wonder, what fundamental piece of this incredible puzzle are we going to discover next?